Our next topic in 0005 is functions, and in this video we're going to look at the definition of a function. We're going to look at some of the vocabulary and concepts that get used when we discuss functions, such as the domain and the codomain. We will have a go with the formal definition of a function. We'll look at what it means for two functions to be equal and some slightly surprising consequences, and we're going to introduce the identity function. So let's begin with our definition here of what a function is. We have a formal definition right here, which is that a function or a map from a set x to a set y is a definite rule which associates to each element in x another element in y. And typically we'll give our function a name like f, and then we'll think of our function f as associating to each element little x in big X, an element written like this, f brackets little x in y. So I'm sure you're all familiar with examples of this kind of thing. For example, we might take, just remind ourselves that Z is the set of all positive or negative whole numbers. So it includes things like -2, -1, 0, 1, 2, and so on. And N, the natural numbers, is the set of all non-negative whole numbers, so 0, 1, 2, and so on. So, for example, there is a function f from z to n, given by the rule f of x equals x squared. So, with this definition as I've written it here, the set x is called the domain of the function f, and the set y is called the codomain of the function f. So in our example over here, z will be the domain of our function and n will be the codomain of our function. And there's a little bit of notation which is used all the time. So when we write f colon x and then an arrow to y, what we mean is that f is a function whose domain is x and whose codomain is y. All right. So there's a little bit more vocabulary that tends to get used when we talk about functions. They're so common that there is a lot of language that's used when we talk about them. So let's just try and get that written down. So let's suppose we have a function f whose domain is a set x and whose codomain is a set y. Then for each element little x in big X, we get an element f of x, which is in y. Okay, so when we have this situation, what we will often say is that the x here, that's my arrow is pointing to that x, that is called the input or the argument to f. On the other hand, the output or the value of f, that is f of x itself. So this thing f of x is the output or the value of f when it has input or argument little x. So this vocabulary of input and output, or of argument and value, this will be used very commonly all the time. All right, so I mean, thinking a bit critically about this definition of a function, it's a little bit vague because it talks about a definite rule, and it's not really clear what a definite rule is supposed to mean. So it's lucky for us if we're a bit skeptical about this definition that there is actually a more formal definition of function which makes precise what we mean by a definite rule. So let's take a very brief look at this formal definition of a function. We're not going to deal with this extensively in 0005, so you don't really have to worry about this. But I think this is a really cool definition, so we're going to briefly touch on exactly how it works. So the formal definition of a function is that a function consists of three things. So number one, a domain, x. Number two, a codomain, y. And number three, a subset of the Cartesian product of x and y. So x cross y, which we defined, you'll remember, in the last lecture. And that subset can't be any old subset. It has to have a specific property. And the specific property is that this subset of x cross y consists of exactly one pair x, y for each x in x. So given such a subset, and given a codomain x and a domain x and a codomain y, we'll actually write f of x for the unique element of y such that there is a ordered pair x f of x in f. So the definition, the condition about this subset f of x cross y is that for each little x and big X there must be exactly one pair x, y in our subset of x cross y, and we just give the name f of x to this element y such that there is a pair whose first element is x in our function f. So it's a little easier to understand what's going on there if we look at an example. So let's take the example which we might, in our informal definition, write as f from n to n given by fx equals x plus 1. That's the rule in our informal definition. So as a set of ordered pairs in the formal definition, this would correspond to, so let's have a corresponds to arrow. This would correspond to a subset of n cross n, and the subset is all the input-output pairs for this function. So for this function we would have the set of pairs 0, 1 because f of 0 is 1, and it would have 1, 2 because f of 1 is 2, and it would have 2, 3 and a whole bunch of other things as well. Okay, so in the formal definition of a function, the way we describe a function formally as its set of input-output pairs. As I say, we're not going to use this formal definition very much in 0005, but I think it's a clever way to capture the idea of a function, and especially to make it precise, so to get rid of the vagueness of what is a definite rule. Okay, let's move on to this slightly interesting question of when are two functions equal. So, I mean, we have to make a definition. We can't, there's no magic place to get to the meaning of equality for functions from. We simply have to make a definition of when we consider two functions to be equal. And in 0005, here's our definition of the equality of two functions. Two functions f and g are equal if and only if three things hold. So first of all, they have the same domain, and let's give that domain a name. We'll say that their common domain is x. Secondly, they have the same codomain. And finally, they have the property that for each little x in the domain, f of x and g of x must be equal. All right, so let's consider some examples just to get a handle of this definition of equality of functions. Let's take a function f, oops, wrong pen there. Let's take a function f from, well, let's have the function that we took earlier. So f from z to n, where the rule for this function was f of x equals x squared. Okay, next function g from, what are we going to do? Z to z given by g of x equals x squared. Okay, so the question is then, is f equals g? What do you think? Is it true or not? Pause the video if you want to think about it. Well, all right, easy one. The answer is no, of course. They are not equal. If two functions are going to be equal, they've got to have the same domain and the same codomain. These two functions do not have the same codomain. The codomain of f is n, the natural numbers. The codomain of g is the integers. So it doesn't matter that they have the same domain, and it doesn't matter that they have the same rule. They have different codomains, so according to our definition, they are not equal as functions. All right, let's look at now another example. So this time I'm going to take two functions, f and g, defined as follows. So we're going to have f and g, and they're both going to be functions from the set containing 0 and 1 to the set 0 and 1. So we're going to define f by giving it the rule f of x equals x squared. And we're going to have g, the rule for g will be that g of x equals x. And so we're now going to ask the question again, is f equals g? What do you think? Again, if you want to think about it, pause the video, think about it. You've got the definition of equality of functions written up there. Does the definition of equality apply for these two things, f and g? Okay, well, I hope you did do that, and I hope you also decided that the answer was yes, because this time these things are equal as functions. So why is that? Well, look at the three parts of the definition of equality of functions. So first part, if two functions are going to be equal, they've got to have the same domain. Well, this is true for our functions. They both have domain equal to the set 0, 1. Okay, next part of the definition of equality, they've got to have the same codomain. And they do. Both of these functions have codomain 0, 1. And the last part of the definition of equality is that f and g have to have the same output for every input in their common domain. But the domain only consists of 0 and 1. And if you just check each of the elements in this domain, f of 0, that's 0, and that's also equal to g of 0. F of 1 is equal to 1. 1 squared is equal to 1. And that's the same as g of 1. So f of x equals g of x for all x in the domain of f and g. Okay, they had the same domain, the same codomain, and the same input for the same output for every input in their common domain, and so they're equal as functions, even though the rules look different. Okay, so this might be slightly surprising, but it's important to keep examples like this in mind because they keep us on our toes, and they're useful because they clarify what it means for two functions to be equal. All right, moving on. Let's now talk about a particular example of a function. So this function is called the identity function, and it comes up very, very frequently. So we have a special name and a special notation. So we take any set x and then we have a special function called the identity function, which we write as id sub x. That's a function from x to x, and it's the function whose rule is do nothing. So the identity function applied to an element little x of big X is just little x again. So it's the do nothing function. This turns out to be very important. We use it very often, so we have this special notation. And in fact, it's used so commonly that you will often see alternative notations as well. So we will sometimes write just the identity from x to x instead of putting in the subscript x. So when it's clear what function, what set we're talking about, we'll sometimes miss off this subscript x. All right, and lastly, sometimes you might even see somebody write 1x to mean the identity function. I will never do this, but you might see some people do this. So this identity function is a good example of a function, and it's one which we're going to use quite often in 0005.